So there are these programs with sub-millimeter facilities, not only ALMA, trying to observe the molecular cloud population of our galaxy and nearby galaxies. One example is FANGS in external galaxies, and we are performing this ALMA-IMF Large Program that is essentially observing molecular clouds, a sample of massive molecular clouds in our own Milky Way. The idea is that, well, in external galaxies, of course, you can observe larger populations, but not with as much detail as we can do in our own galaxy. Whereas, well, we have a full ALMA Large Program to observe only 15 clouds in the Milky Way, but we observe them with very great detail. And as they evolve in time, they evolve into these stellar cluster populations that are already optically visible, and one can see the entire stellar population also in the near infrared, and what we are observing the very embedded clouds. No? And of course, one can do these things also with extinction, not only with molecular with sub-millimeter facilities, no, but extinction and optical data also gives a lot of complementary information. So. So I know I will try to be fast, but I saw I needed a robust introduction. I see there are several students among the audience. In the radius of millimeter, we see a variety of emission processes. In the continuum, we are dominated, and I'm talking about centimeter, millimeter, sub-millimeter wavelength. So if you think in terms of frequency, say from 1 gigahertz to hundreds of gigahertz, we see a variety of emission processes. The continuum is dominated essentially by emission from plasma. If it's thermal, it's free. If in magnetized regions, we can have synchrotron radiation. And the favorite of everybody is the dust emission, but we will see that sometimes it's not straightforward to think that when we have an ALMA map, it's dust. Unfortunately, it's often the case that when you see an ALMA map is dominated or heavily, quote unquote, contaminated by free emission. That's the continuum. Luckily, that's thanks to nature, the optical depth of dust and free emission in this regime has an opposite behavior with frequency. So this means that with multi-frequency observations, we can separate the emission processes. No, so this is a map that a student working with me, he produced this for the entire ALMA-IMF sample. So essentially, with the spectral index between two bands, you can separate the emission from the free emitting regions, the ionized gas, and the emission from the dust, and even see the tiny H2 regions embedded in the dust, just from the combination of two ALMA maps. No? Essentially the radius to sub-millimeter SED. We also have emission from lines, you know, especially molecules have the rotational transitions in the radius and sub-millimeter. So this type of observations is the workhorse to observe in spectral lines the content of cold molecular gas in the universe, no? In local regions, in external galaxies, etc. So now related to star clusters, so we make this sometimes artificial distinction between low mass and high mass star forming regions. The truth is that probably processes are similar enough that we shouldn't make a distinction. But it's true that to observe massive stars information, you have to observe very dense, not only very massive, but very concentrated molecular clouds that are able to form also massive stars. No? And this is the type of thing that we are doing since when we were PhD students. So these are observations from my PhD or when I was transitioning to the postdoc. This is also a colleague, Baobab Liu in Taiwan. So essentially, we observe these very massive clouds. We try to observe them with single dish and interferometers. On that time, it was the SMA These are the pre-ALMA days to try to observe the molecular cloud structure from this cloud that is forming a star cluster. No? Then if you zoom in to the individual star forming cores that are forming presumably a single star, probably a binary, there is a different behavior between low mass and star forming cores. There is a real distinction in the sense that only the cores forming high mass stars eventually produce H2 regions, no? Because if you only form a star that the final stellar mass will be like 2 solar masses, you will not have enough ionizing photons to affect the environment through ionization. But in those sites where you end up forming something about 10 solar masses, so you end up forming an H2 region that ultimately affects the entire cloud. No? So that's an important distinction. And of course, now we are very interested in understanding the origin of stellar masses. I am not a stellar astrophysicist, but there are several stellar astrophysicists here. But well, the single most important property of stars is the initial mass, no? Followed by properties like rotation and abundances, etc. But the initial mass is the single parameter that is most relevant to understand the life and death of stars. No? So now we are running, of course, there is this idea of the IMF. It can be universal or not, but certainly it follows a function that has decreasing numbers with increasing mass across the universe. No? The exact slope, etc., is controversial, but yeah, we have very few massive stars compared to low mass stars. So now we are running these ALMA programs to sample the population of star forming cores. So the idea, you know, there is this inherent stochasticity in the process. The idea is that if you want to understand how do you form, say, an Orion with a few massive stars, you can observe a cloud like this one, let's say G33, that has a few star forming cores that will form massive stars, no? Whereas if you want to form something like probably I'm exaggerating because there's nothing in the Milky Way as massive as R136, which is the star cluster in the Magellanic Clouds. Well, we have a few embedded clouds in the Milky Way that are forming stellar populations with probably a few times 10 to the 4 solar masses in stellar content. This is W51 is one of them. So we essentially need to observe the densest, most massive star-forming clouds in the Milky Way to sample the core population that will form a massive star cluster, no? And that's what the ALMA-IMF program is doing. So I will introduce first this program. It's an ALMA program that we've been working. It was a pandemic project, so I think in previous talk I showed the very sad picture of all of us in Zoom, no? Having our conference in Zoom. I don't show that picture anymore, but it is a program that most of the data reduction and essentially all the data intensive work was done through Zoom, no? Remotely, and now finally we can meet in person. The PI is Frédéric Mott in France, and these large programs, they need PIs from all the areas of ALMA. So there is one American PI, Adam Ginsburg, and Japanese PI, Patricio Sangüesa, is actually from Chile, but he works in Japan. So, you know, the globalization of science. So it's a large structure, there is a management team, etc., data reduction. So we are divided in areas. I participate in most of them, and I'm in the management team. So the idea is to observe these 15 protoclusters. They are Atlas-Gal selected. Atlas-Gal was this survey, single dish survey of the galactic plane. So essentially, we have the mass of the star-forming clumps from the single dish sub-millimeter continuum. So we selected the 15 most massive clumps within 5 kiloparsecs of the sun. So in a sense, it's like a volume limited sample, no? And then we observe it with ALMA in 2 array configurations to have good UV coverage and good image quality, and in 2 bands, no? So we have 3 millimeter data and 1 millimeter data, both continuum and spectral lengths. No? So, you know, these things, they produce a lot of a lot of things. But I will talk mostly of the works that I am mostly involved in, which are actually the data processing. So I will bore you with a lot of details on interferometric data processing, and a few of the first results of the core mass function. Nicole Cunningham, she will just move to Manchester. I think she will start in the SKA in Manchester in the next few months, and she led the paper on the line data release paper, which just appeared a few months ago. The data release of the interferometric data processing. So we make the large programs have an obligation of liberating data to the community. So the continuum interferometric data is already available through Zenodo, and the pipeline is also available through GitHub since a while ago. The pipeline actually permits to make semi-automatized continuum self-calibration of mosaics, which is something that not even I think the ALMA as an observatory just recently liberated a capability to request automatized self-calibration of ALMA observations, but I think it's for single pointing. So this pipeline can be used for mosaics. Probably it's not as nice as the service of an RAO, so one needs to get into the code to understand things, but it works, and we have already used it for one project beyond ALMA-IMF. So it's possible to use it for mosaics from other projects. And most recently, a student of mine working in Mexico has also liberated the combination of interferometric data with single dish. You know, interferometers by construction, they are not sensitive to the largest scale emission because they are interferometers. So they are Fourier filters, so they filter the extended emission. And ALMA actually does not offer single dish observations for continuum data, because the antennas working as single dishes, they have heterodyne receivers, so they do not serve as multi-pixel continuum mapping machines. For that, you need a bolometer camera, so that, you know, you have a bolometer camera on the GBT, in other single dish telescopes, in the IRAM telescope, etc. So you need to combine a continuum image from a single dish obtained through other projects with the ALMA-IMF data, no? So Daniel did that, and they accepted the paper recently, so it's already on arXiv, and that is public as well, so people can grab it and use it. The line data, I think this was the most heaviest in terms of data processing. The raw data of the project is about 10 terabytes, but of course, after processing, it can go one order of magnitude above. And then it's like making coffee, no? So in the end, I mean, the few drops that come out, the data products are a few terabytes. So for the line data, the data products are hosted in Dataverse, in Harvard's Dataverse, not in Zenodo, because they allowed for bigger files, no? So it's also already available. The computer that has everything is Adam's computer in Florida, no? But we in Morelia, and also computers in Grenoble, we during the process we were at some points hosting like a third of the 100 terabytes that I mentioned here, no? So I have seen some IFU projects in the optical that they talk in terms of pixels or spectra, no? If one makes the exercise for this, we have something like 10 to the 13 units of data, no? But you know, interferometer data in a way has been like IFU data since a while ago, no? In the sense that we have the 3D information, no? The position and velocity cubes, even polarization, but we don't have polarization information by default. So the catalogs of scores are being released. They are identified through, this is something that there are several, you know, structure identification algorithms The ones that we use are two of them, which give consistent results. GetSF by Meshinkov et al. This was heavily used in the Herschel surveys, so it comes from the Herschel community. And GetSources, which is an algorithm by Sylvain Bontemps. I personally, I also like using dendrograms. So with my student Daniel, we also use dendrogram identification, and things are consistent. But there is this, because of course the gas in these clouds is a continuum, no? So the identification of peaks, of course, will have some sensibility to the parameters of the identification algorithm that we use. But given that, so we are releasing these catalogs, of course. And Nicole, I was discussing this a little bit yesterday with Mike. The catalog, of course, has a very superficial analysis of the dispersion of the velocities of the individual cores in the protocluster clouds. But in a way, this data set is complementary or similar to this very impressive. I mean, when I see Gaia results, when I see Gaia talks, I get amazed, no? Because now they have the capability essentially of measuring if a young star cluster is a coherent unity, or if it's contracting or expanding, etc. So we don't have proper motions, but we have the line of sight velocity, no? And the objects that we detect are younger, no? They are not bare stars, but they are star-forming cores, no? So I think this information is complementary. Details of the data reduction. We had to develop a few things that are not even included in CASA for those people interested in. For example, there is this issue with the so-called Jorsaten and Van Morsel correction, no? Which is an issue with when you make an ALMA image or a VLA, an interferometric image, the PSF with which you reconstruct the image is a Gaussian approximation of the real PSF, which is not Gaussian, no? That means that there is an inconsistency between what is your model, your deconvolved model, and the residuals. The residuals is this map of residuals, the thing that the convolution algorithm never touched, no? So, and in the end, you add them up, no? So there is an inconsistency in units because your model is in Jansky's or in flux per clean beam, whereas your residuals are in flux per dirty beam. As long as the residuals are small compared to your clean model, that doesn't matter. But if for some reason your residuals have a good fraction of the flux, this matters, no? And somehow this is not implemented in CASA. So the recent ALMA large programs, they had to deal it with themselves. The scripts that we use to make that are also freely available to the community. I mean, we need to make like a nice Python package out of them. Now it's a mess. I mean, they are not documented, etc. But they can be used if needed to fix this problem that is not implemented in CASA, no? The software that we use to make the images. Things like that, no? Now, to separate the free contribution, I already told you, one can use the spectral index, essentially the color, if you want, between the two ALMA bands to separate free and dust. But there are other ways besides the free. The classical way, actually, what most people do since a while ago, is to also take a centimeter data observation. For example, you have an ALMA program, you want to separate the contribution of dust of free. So you observe with the VLA, and the VLA is dominated by free, and you assume a spectral index for free and extrapolate it to the millimeter map and subtract from there. That's possible, but especially in star-forming regions, you will find this type of very young H2 regions in which the spectral index of the free is not flat, but because the H2 region is still very dense, and you could still have density gradients within the H2 region, the spectral index of the H2 region will be a bit positive. So then if you assume a flat SED for the H2, it will give you wrong results, no? So then you can combine these approaches and use a third approach that I'm preparing a paper within ALMA-IMF with this approach. Within the many lines that we have in ALMA-IMF, we have also recombination lines. Just like we have optical infrared recombination lines, radio recombination lines are very useful. In particular, in the ALMA-IMF data, we have H41 alpha and H30 alpha. The H41 alpha is the cleanest of the two. So we can take the millimeter recombination line and essentially from the LTE line to continuum ratio that the recombination should have to the free continuum, we can calculate what the free continuum should be and subtract it to the observed continuum and obtain a map of pure dust. No? So that's the idea. So this shows this is the prediction of the free continuum obtained from the recombination line, and this is the map of the free dominated areas in blue versus dust dominated areas in red obtained from the spectral index approach. And you will see that both they give consistent results. This is atomic physics, no? It's not astronomy, no? But the issue is that the recombination line is less sensitive. So it's true that the recom line will not give you the free estimation in where the H2 region is the faintest. But for the brighter areas, it will give you an estimation of the free flux in there. This is just an issue for a fraction of the ALMA-IMF fields, the ones that are more evolved and that have already H2 regions. The younger fields without H2 regions, they have been analyzed first. So you will see, if you check the publications, you will see that the first scientific results, they focus on the younger regions, the ones that do not have this issue of free contamination. No, that's the situation. So this is the validation of the procedure. In the y-axis, we have the pixel by pixel, the prediction of the free content from the recombination line, and the x-axis, the prediction of the free content from extrapolating from the continuum from the centimeter in one field in which we have good data both from the VLA and ALMA. And 96% of the pixels are within the one-to-one relation. And we have a few outliers that most of them are actually these H2 regions that I was talking about to you a few minutes ago, that they are very young H2 regions where the free is not optically thin. So they are partially optically thick H2 regions that behavior extends all the way to 3 millimeters. So that's right. So now a little bit of science. Those are all the data and say processing challenges. No. So a few scientific papers have been published from the consortium. I will highlight a few results. For example, in the least evolved fields, the ones that do not have free contamination, we are getting consistently that the CMF, the core mass function, the mass function of these peaks that will form stars, is consistently has a shape that is flatter than the salpeter IMF, which in this logarithmic representation would be -1.3, not -2 because we put it in logarithmic, no? So this would be the salpeter slope, and this is the bootstrapped CMF from the W43, which is a subsample of the project fields. Now, what's the origin of that? So Tomà Noni, a postdoc that was working with me until recently, now he moved to Italy. The work of Tomà Noni, well, the main thing that he did was to take again these young fields that are more easy to study and identify bipolar molecular outflows in them. So then one can separate the core population in two types: the protostellar cores, that is those driving an outflow, and not only outflows, but also if they have any obvious sign of protostellar activity. If we identify something called hot molecular core emission, so essentially you see tracers of very saturated organic molecules that you would only see that line if the gas is heated to a few hundred Kelvin. So that's a sign of protostellar activity or a protostellar outflow, etc. So you identify all the outflows with protostellar activity, and you separate them from the outflows from the cores, sorry, without obvious protostellar activity. So then we have protostellar cores and prestellar candidates. We cannot say for sure that they are prestellar cores because they could still have something very weak hidden, no? So we have protostellar cores and prestellar candidates, no? And separate the CMF of the two of them. And then it turns out that is actually the protostellar ones. So this was a bit like the opposite of what we expected, but that's the way it is, no? The protostellar ones are the ones that have an excess of massive objects, no? So and it's the younger ones, the ones that are consistent with saltpeter. What's interpretation of this? One possible interpretation is but we need to quantify hydrodynamical simulations to understand this, to make synthetic observations of hydrodynamic simulations. So I think the idea is that you favor this type of here in the British community. I mean, actually, they started here the Bonnell group and Matthew Bate, etc. And essentially all the type of simulations where the stellar population that is forming co-evolve with the gas in their surroundings, no? So essentially the cores continue to evolve in mass as together with the protostellar accretion, no? That would be the idea. So currently the simulation that we do is a drawing, no? So it's a drawing made by Adam. So you essentially make you have a protostellar core that has a lot of accretion from the environment, and the prestellar core for some reason appears to be on average less massive, no? So this would be the situation, no? So the gas content evolves together with the protostellar content, no? So that's what we have now, no? I'm doing more stuff with the H2 regions, no? So the H2 regions are not useful only to separate the free from the dust, but the H2 regions themselves can be used to make some science. For example, here we measure, because we also measure the helium recombination line, so we can essentially make nebular abundance estimates like they are done thoroughly in optical astronomy. So this is the helium content per ALMA-IMF field. So we get the typical, the expected 8%, no, by number from helium to hydrogen. But we have a couple of outliers, one with a very small content of helium, and one with a very large content of helium. And we are thinking in ways of interpreting this. Yeah, I will not bore you with that, but yeah. So yeah, so there are many things to do with the evolution of H2 regions. One obvious thing that the H2 regions can be used for is to try to quantify protostellar feedback, no? So we have the population of protostellar outflows, the population of H2 regions. So we should try to say something on the magnitude of the mechanical feedback from the two types of feedback objects that we have inside the clouds. So these are velocity maps, etc. But we are just analyzing all this. Something else that we are doing, and we started to do this in W49, which is not part of ALMA-IMF because it's further away than the distance that we set. But we have data in W49 apart from ALMA-IMF, is to try to use the free data to quantify the embedded stellar content of the clouds. So the idea is that if you see the typical VLA paper from since the 80s, typically one only reports until an estimate of the amount of ionizing photons, no? So we have the free object, and we can estimate the amount of hydrogen ionizing photons from the free object, no? But then the question is, what if we tie this together with stellar calibrations? I know these stellar calibrations are done in the optical, no? like the Panagia and Baca, and most recently the Martins, etc. No, all these stellar calibration models that give you some estimate of the spectral type, stellar mass, etc. If we have the number of ionizing photons and we tie together the stellar calibration, we can probably obtain the distribution of stellar masses of objects that are embedded, no, that you only see them in the radio, no. So for the most part, these are not sources visible, not even in the near infrared, no. Some of them will be visible in the near infrared, but most of them are not, no. So that's the type of game that we are playing. So Mariana Juarez has been working on this. So the idea is to have a prescription to retrieve the distribution of stellar masses with some estimation of the error based on the error of the stellar calibrations from the radio continuum. So that's the type of thing that. So ideally, we will have not only the distribution of core masses, of the gas core masses, but also where this is only sensible to massive stars. We only observe stars more massive than 8 solar masses with this method because we need to have the free, no, the ionized gas. But some idea of the stellar content, and then of course the thing that would complement all this would be to have JWST data, no. But it's very difficult to get proposals approved for the JWST, no. So, but ideally one could have the full stellar population combining the two things, no. Yeah, we can also put it together with isochrones, etc. So just to finish, we are also trying to do synthetic observations of things. So we have this little code that has grown a little bit to make analytical models of objects like outflows, jets, envelopes, disks with the envelope, etc. And Andres Izquierdo was working with me. Now he moved to PP Disks, so he's making the PP Disks PhD in Leiden and ISO. But when he was working with me, he made this code. So the modeling code can be plugged in to radiative transfer codes that are also public, like LIME, Raven C3D, Polaris, etc. So one can make synthetic observations of essentially of ALMA observations, no? So you have a model with several protostars, and now this is getting very fashionable, but we left the topic, no? This study of streamers. So I think there is even a NOIMA Large Program to look for streamers, no? And we abandoned this thing. So essentially you have like a flow of gas that you can model as a free falling. In this case, it was a parabolic trajectory. So you can model it as a free falling flow of gas that feeds a protostellar system, no? And you can make the synthetic observations. In this case, we made synthetic observations of the methyl cyanide, the CH3CN molecule, which here on Earth is used a lot of for insecticides and things like that. No, but yeah, in the ISM it traces dense gas. And currently, Miguel Jaques is working on radiative transfer, but of hydro simulations. So we took some simulation of the Enrique Vázquez Semadeni group in our institute, and made synthetic observations, or in this case of Herschel far infrared observations. No, so Miguel passed a season in Belgium with a group of Martin Bayes. They have this skirt radiative transfer code to make dust observations. No, so we are trying to do that to try to work a little bit more with theorists and try to extract observables from the simulations. No, that's the program, no, that we have. And I work with recombination lines, so the things that I do as first author have to do with modeling ionized emission. No, so we are modeling this ionized disk. This is a very special system. The central mass is above 100 solar masses. We are not saying that it is 100 solar mass star information, but it should be something like a small system with 340 solar mass stars. You have enough gravitational pull to actually make this is an ionized disk. No, so it's a system that within a few thousand AU the H2 region is still gravitationally bound. So the H2 region has some rotation motion, even if it's ionized. No, it's like a gravitationally bound H2 region. No, so these are very special systems. Yeah, and so I think just to finish, so we are. I know probably I should be careful to come to Britain to talk about the NGVLA, but I think now the two projects are more friendly. Actually, they hosted a joint conference recently, an NGVLA SKA conference. I know Tyler Bork and several people from the SKA community but in Mexico, we are trying to get involved with the NGVLA for obvious reasons, because the idea is that a few of the antennas, it's only a few antennas, but they are very important because they provide the long baselines of the mid-array. The idea is that they will be within Mexico, no? So we are starting to work with local state universities in Sonora and Chihuahua and Nuevo León, essentially in the states in the north of Mexico, to look for sites, etc., to make this a reality, no? And UNAM, the university where I work, has already signed an agreement with NREO, and we hired a joint postdoc that is actually doing this work and also simulation work. So yeah, so that's the idea. And this is not the real sign of the NGVLA. We just put the sign of the Mexican flag in the real logo of the. So synthesis imaging in one slide, no? So we have something called the visibility function, that is an ideal visibility function, but sampled over essentially over where we have antennas. And if you Fourier transform your sampling function, you have your PSF, and your observation is actually the Fourier transform of your measurement. So ideally, we have these deconvolution algorithms that try to eliminate the shape of the PSF from your ugly, dirty observation to try to recover something closer to the ideal truth. This is important because one of the things that we are trying to show, and we are preparing an NGVLA memo that should come out in the next few months, to show that actually by adding the antennas in Mexico, you not only improve the angular resolution, but you improve the shape of the PSF. No, you have here two examples, no, that show at different declinations that the shape of the PSF is essentially significantly improved when you go to the south. No, so yeah, so it's something obvious, but we are trying to quantify it to show that those antennas are actually needed. And with the tools that I show you, we are also doing, we are helping on the science case. So we are essentially making synthetic observations of systems that currently are undetectable or unresolved by the VLA, to try to make predictions for what the NGVLA will see in the context of star formation at high angular resolution. So essentially we can resolve radio jets and young H2 regions, and not only the continuum, but the recombination and kinematics in essentially from very small mass objects to very massive objects. Yeah, and even you can have something like self-obscure disks, but in ionized gas. In maybe Sourceye will be a good example for that. No, but that's at the center, the free should be so dense that you should have this sort of self-obscuration at the small scales. But yeah, let's see if that prediction is actually true. So we are hosting the next NGVLA conference in Morelia, actually in November 2024. We are trying to compile the SOC as we speak. This will be the third international conference of NGVLA. So that's a big change. I mean, the first one was in Manhattan, in New York City, the second one in Vancouver. So the third one was either Mexico City or Morelia, and some of the organizers decided Morelia. So it makes sense because our institute is there. So we will send the first announcement in a few weeks. So for interested people, it will be distributed. And I will leave you with my conclusions. That's all. Thank you.
Thank you, Roberto. Any questions?
Yeah, we're worried, like you say, a bit more about how how IMF regions are selected, third atmosphere are selected.
Yes, essentially. So Atlas-Gal, is a galactic plane survey at 870 microns, so in the sub-millimeter continuum. So we selected the most massive clumps within a size of a few parsecs, within 5 kiloparsecs of the sun. That excludes a few very extended regions like Cygnus X. No, Cygnus X has a lot of mass, but is distributed across tens of parsecs. So it is very distributed. No, so we effectively ended not only with very massive clumps, but with very dense clumps. So you have to have that say 10 to the 4 or more solar masses of gas, but within a few parsecs. The size of the ALMA-IMF mosaics is always a few parsecs in size. So we are effectively the size of all these mosaics, it will be a couple of parsecs across. No? So actually there is a bar here, 0.1 parsec. So the total size of the mosaic will be a couple of parsecs. Yeah.
Was there any kind of selection in regard to whether there was star formation already happening that you could see in the infrared, for example, or was it just purely ignoring the fact that there may or may not be an infrared?
By selection, it was ignored, but then in the data survey paper, the infrared is characterized. Actually, the regions are separated in an evolutionary sequence, which has been questioned. But essentially, we have the luminosity to mass ratio of the clump. And also we have the free content. So the separation in young fields, things that are intermediate and variable fields, is based not only on how bright they are in the far infrared, but also in the content of free emission, everything I was showing. No, so from the two things we separate them in classes. Yeah.
So you showed the images where you're able to very nicely pick out the outflows from the third stars. And I was wondering if that provides any information about the contribution of the outflow energy as
Yeah. This paper doesn't. We haven't published anything on the mechanical feedback from the outflows. I was saying that somebody needs to do it. Yeah, and apparently in the last few weeks, apparently I've been volunteering myself. But if I do it, I will put it together with the H2 region information. Yeah, because I am my contribution. I am mostly interested in the H2 region stuff. No, so yes, but we can try to quantify. Something that people complain when you say this is that you don't know for sure the abundance of CO. So we have the outflows characterized in CO and SIO as well. And there is a good overlap, but you have some outflows that you see them in CO, or some others only in SIO. In particular, the abundance of SIO is problematic. That can vary by orders of magnitude. The CO, I would say, my take would be with CO, you can have an estimation of the mechanical input of the outflows. No? So that can be done within an order of magnitude error bar, if you want.
Do you have any rough estimate of the amount of mass in the outflow compared to the mass in the third? They saw this one.
Many of these are so-called massive outflows, so they will have a fraction of a solar mass total only in the outflowing gas. Yeah. But we are sensitive also to lower mass outflow. No? So we will the same way we have massive cores and intermediate mass and low mass cores, we will have some very massive outflows and some other outflows that are coming more from intermediate to low mass stars. It's just that now we can see them at kiloparsec distances. No, Yeah, it's like if you observe something in Taurus or Ophiuchus about that kiloparsecs, no? That would be. Yeah. I think there was one question there. Yeah.
I was wondering about the list of lines that we showed. So it seems to me that there's an awful lot of emission lines
We have more actually.
in this data.
Yeah.
And you say here main lines. So
Yeah.
basically, like, how many lines in total do you have? Are they all identified? And if one is interested in something particular?
Yes, exactly.
The paper,
Yeah, the line data release paper makes some identifies all the obvious lines, but there will be some very faint features or even things that are very difficult to identify. We haven't done that job, but the line data is publicly released, so that can be done by other people outside the consortium. But these are the lines. These are actually the most obvious ones. Essentially, this is a list of the lines that we plan to analyze as a team, no? But the cubes have many more lines, and that actually depends on the region. Some regions are richer in more complicated molecular line emission, whereas I don't have the fits here. For some others like G333 or the W51s that are more evolved because they already have H2 regions that are breaking apart everything. If you see the spectra in the cubes, you will see that they are not as rich in molecular line content. So yeah, so some lines have a line forest, like really probably thousands of lines whereas others will have a few tens of lines. Yeah. So that's the typical situation with ALMA data these days. So one observes with ALMA and one has many molecular lines that never get analyzed.
well,
That's-
first time I've actually seen helium recombination lines personally. So are there any other elements that you have as well?
I looked for carbon without success. Yeah, that's something that if you talk to that was more interesting to the VLA community, no? If you talk like to very senior radio astronomers coming from the centimeter radio astronomy, there are some classical papers on atomic recombination lines, etc., from other elements, etc. And now the ALMA community, I would say typically is not interested in hydrogen. So they see it as a burden, no? It would be nice if the map would be entirely dust, no? So you have the ionized gas there bothering your observation of dust. No? That's the situation. Yeah.
Thanks.
Yeah. Thanks.
One more question.
So based on these first results of the ALMA-IMF program, what's your take on concerning the physical meaning of the CMF and the link to the IMF? So you find this interesting difference between the prestellar, the protostellar mass function.
Yeah.
Does that mean that there may be a single process that is perhaps dominating the shape of the CMF, or is it still the case that one could argue that maybe there's so many processes at play still that it's
Yeah.
the limit theory a thing that determines the slope eventually?
My personal take is that it's really difficult to, I mean, that cores are not stars, no? There is a continuous, the gas is a continuum. So like in this hierarchical drawing of Baobab, no? In a way, this is like a Bonellar Bate or Enrique Vasquez simulation. So you will have the cores, but of course they are surrounded by less dense gas, which itself is surrounded. So these measurements are important, but are not the ultimate truth, and we need to calibrate them with synthetic observations from simulations. So the core will not be something isolated, but in a way, for example, the top heavy core mass function that we are measuring in protostellar cores maybe has to do with the fact that the segmentation algorithm, when you observe a protostellar core, let's say this one, the identification algorithm is drawing the contour in something that contains an envelope. Like the core has an envelope, no? And something that contains an envelope. Whereas in the prestellar, they are probably more isolated imagine you have one of these orange things here outside, no? So the contrast will be larger, no? So there is a bunch of ideas circulating there, but nobody leaves the time to actually do it, no? And one idea, for example, would be to some cores are partially resolved. They are partially resolved, no? Essentially to see the profile, the radial profile of to repeat the Tomanoni paper, but stack profiles, no? So and probably you will see that the border of the protostellar cores will be less, the contrast will be less, so it will be less obvious. But some people take this explanation like, you are saying that the core mass function is an artifact. No? Well, it's not an artifact, it's just that the gas is a continuum, no? So we are also trying to push a lot the people working simulations in Mexico but the problem is that their simulations don't have enough resolution. So yeah, we are contacting other people. Before this week, I was in a conference. I talked to some people that to see if they can share a simulation, etc. No, so yeah, that would be good.
I think we'll leave it there.
Thank you.
Again.
Thank you for coming. I